So I'd like to consider the problem of taking the graph of a function and producing from that graph the graph of the function's derivative. So I've come up with a nice example of a lovely piecewise defined function here, but before we get into the actual problem, I think it's worthwhile to formalize what we mean by the derivative of the function by f prime. How is f prime related to f? Well, recall that f prime evaluated at c is the slope, and I'll put that in quotes here, the slope of f of x at x equals c. Now, of course, if f is linear, it has a well-defined slope, so this makes sense. But if f is not linear, what I mean by slope is the slope of the tangent line to f of x. So this is really the instantaneous rate of change of the function at the value at x equals c. So how would we approach this problem for the current example of the function here? Well, we're looking for the slope of this function. We're looking for the rate of change. And notice that this function breaks up nicely in 5 different regions, and the slopes are going to be different in each of them. So let's go ahead and, first of all, and identify those regions one at a time. So we have this first region here for x values less than -4. Region 2 for x values between -4 and -2. Region 3 for x values between -3 and -1. Region 4 for x values between -1 and +2. And finally, region 5 for x values bigger than 2. So how can we think about finding the slope of the function in each of those regions? Well, in certain regions, the slope is pretty straightforward to find, in fact. So anywhere where the function is linear, so in region 1, region 2, region 3, and region 5, the function is defined linearly, so finding a slope just amounts to taking 2 points and calculating the slope between them. So let's go ahead and do that then. So in region 1, we have a point here and a point here. In region 2, we can use the same point and this point. Region 3, we add an additional point. And then in region 5, let's pick that point and that point. So these are on the grid. The slope should be easy to calculate. Good. So in region 1, notice that going from this point to this point, I'm going to go up, what is this? Up 4 and to the right 4. And that tells us that our slope in that region is equal to +1 because the rise and the run are equal. For region 2, in going from this point down to this point, I'm going to go down, what is that? Down 5 and to the right 1. So that tells me that my slope in that region is -5/1 or -5. Region 3, we don't even really need to look at these points. We can tell that since the line is horizontal, the slope in that region will be 0. And then let's skip region 4 for a minute because we clearly have some nonlinearity there. In region 5, going from this left-handed point to this right-handed one, we're going down 2 units and to the right 4 units. So down 2 to the right 4 is a slope of -1/2. So the slope in that region is -1/2. Good, so let's go ahead and graph the information we have. We know something about the derivative of f in regions 1, 2, 3, and 5. And notice that those regions have, their own domains. So region 1 has this domain. Region 2 has a small domain. Region 3, and then the domain of region 4 is everything bigger than x equals 2. So let's go ahead and plot these derivatives. Let's plot these f prime values on the right-hand side. So for x values less than -4, we will have a slope of +1. So a slope of +1 is going to be here. Less than -4. And we're going to have an open circle right there on the right-hand side because, well, my tangent line is not well defined at that corner, so the slope of the tangent line won't be well defined either. Notice that region 2 has a very small domain from -4 to -3, which is over here on the f prime graph. And then I'm going to have a slope of -5 in that region. So let's go ahead and find that. -5 right there. And again, we're going to put open circles at the boundaries for the same reason. We have corners, and tangent line is not well defined there. Region 3, I have a slope of 0 between -3 and -1. So -3 and -1, right there and there. And let's put our open circles for the same reason. And then in region 5, this is where x values are bigger than 2, and I'm going to have a slope of -1/2. So -1/2 for x values bigger than 2. It's going to be like this. And I'm going to put an open circle there because of that corner. Good. So now what do we do with this last piece here, this region 4? Notice that region 4 is not linear, so we can't do the same trick with picking points and calculating slope. But we can notice some points on the graph. So let's go ahead and put some points on the graph of that function in that region. First of all, we have the origin is there. The obvious ones that I put on the left-hand side and right-hand side. And then there's an additional one here, if you look closely, at 1, 1. Now, if you think hard enough, you'll realize that this is the graph of y equals x squared in that region. Y equals x squared. And we know what the derivative of y equals x squared is. It's dy dx, that's the derivative of y with respect to x, is 2 times x. We can use the power rule for that, right? The exponent comes down to the front, and then we reduce the exponent by 1. So what this says is that this is my f prime of x in this region between -1 and +2. So I can go ahead and graph the function 2x in that region. That's exactly what I'm going to be doing. So in that region, so I'm going to have going from -1, -2 as a point. I'll have an open circle there. And then +2, +4, and I'll have an open circle there, and then I can connect them in between. And this is the graph of f prime of x. As ugly as it might look, you should expect it seeing a graph with lots of corners. Anytime you have a corner in the graph of a function, you're going to have a jump like this. You're going to have all these jumps in the derivative, and that's because the slope radically changes from one side to the next. So you should always expect these.